Shall I start?
Ma'am, let me introduce you first, ma'am.
Sure.
Yeah, I'm
Thank you.
okay, ma'am. We'll start, ma'am. Uh, Good morning, all. We have with us today Dr. Leena Vachani, ma'am. Leena Vachani, ma'am, received her PhD from IIT Madras, India in 2009 in embedded robotics. She is with the Systems and Control Engineering Group, IIT Bombay, Mumbai, since December 2009. She has guided PhDs in the area of embedded control and robotic applications that include topics on multi-agent mapping, exploration, and coverage. Leena Vachani, ma'am, received her PhD from IIT Madras, India in 2009 in embedded robotics. She has guided 3 PhDs as main guide and 3 PhDs as co-guide in the area of embedded control and robotic applications that includes topics on multi-agent mapping, exploration and coverage. She is a recipient of the 2013 Young Scientist Award under Fast Track scheme. Her current research interests are perception modeling for single and multi-agent applications, edge computing for IoT and multi-agent applications for IoT framework. Her current research interests are perception modeling for single and multi-agent applications, edge computing for IoT and multi-agent applications for IoT framework. She is currently leading the activity of establishing Technology Innovation Hub TIH at IIT Bombay under National Mission of Interdisciplinary Cyber Physical Systems. Ma'am's today's topic is Embedded Systems in Robotics Control Challenges. We welcome you, ma'am. I request ma'am to please start the session.
Thank you so much,
Thank you.
Sushma. Thank you. Let me first present my screen and share my screen, and then we can get started perhaps. Yeah. So Sushma, can you help me? What are you able to see on the screen?
Yeah, ma'am, your screen is visible. Now it is gone. It was, yeah, it's there, ma'am.
So you are able to see my PDF window. Am I right?
Yes, ma'am.
And now it is the full screen.
It's full screen. Yes, ma'am.
Okay, great. All right. So as I thought of giving this particular topic on embedded systems and robotics control challenges. So this is basically talking about more or less about the small size robots and what all we require for computing it, and at the same time um, our objective is to make sure that the control laws that we design are such that the whatever theoretical analysis we do about the stability and other stuffs that basically fulfills it, right? So if we start with this, the introduction is already about me is already done. So let's start with how this particular lecture is designed. So I'll be speaking for 45 to 50 minutes and kept the discussion time for last 10 minutes. But at the same time, you can interrupt me any moment of time, and I will try to answer it. Instead of keeping it one way, I like giving it two ways. So in this particular online mode, I would request Sushma to interrupt me if there are any questions on the chat window or somebody wants to unmute and speak.
Sure, ma'am.
Right. So thank you so much. So now to begin with, I will speak about first of all, what are the different embedded platforms, and from the controller perspective, what all aspects we should look into when we are choosing a particular kind of an embedded platform. Then in the second part of this, following that, I will speak about a design methodology that we used for the for solving certain robotic problems, especially collision detection and avoidance. And that methodology is interval analysis. I will motivate you why did we choose it, and let's see if you can develop further problems, robotic related problems using interval analysis. The third part of this will talk about certain bottom-up approaches for the embedded systems, where we do not choose the embedded platform first, and rather look forward for designing the control law, and then implement in it should be implementable in any primitive embedded platform, right? So let's start with embedded systems, what we are talking about as a controller. So when we talk about the embedded controller, it's a very straightforward way of looking at what we are saying as an embedded controller here is something. For example, this is a robot. This block diagram is for the robot. Robot embedded controller, the embedded controller designed for the robots. So your system is nothing but a robot, and whatever you are able to sense it, that you are feeding it to the controller through the sensors and the ADC channel. Similarly, what are the control commands being generated that you convert into DAC, amplify it, and give it to the robots? If the input to the controller, input to the robot is itself digital, then you don't need this DAC channel and so on. But that will be dependent on what kind of programming and what kind of methods you are using it for this. So for example, you are basically giving the commands for the motors to run. So those commands can be digitized. I mean, you can look forward for PWM methods and so on. In that case, you are basically removing this DAC part to the PWM generator and so on, right? So a good interface is required when you are solving the controller problem, when you're implementing the controller into the embedded platform. So when we look into designing the control laws for the embedded platform, and at the same time when we have chosen that, okay, our controllers should stay in an embedded platform. So what is the advantage that we get? The advantage that we get is a smaller semiconductor area. You are able to do the control system design. You don't need bigger computers and so on for computing. So you are basically saving on the semiconductor area. And our objective is anyway to look forward for designing for the small size robots. So why do I have the communication with a bigger system? The laptop or any other computing system cannot be placed at the robot itself. So one has to look forward for designing it with some embedded platform, which is part of the robot's processor itself. Low power consumption, because that is something which you are looking forward for your battery life, your battery requirements onto the robot. That is also going to be carried by the robot. So finally, you look forward for small size solutions, not only from the processor perspective, but from the interfacing as well as its added power requirements as well. So in all, one should look forward for getting a small size for the robot designs. One should look forward for its availability in the market, should be easily available as in the bulk form, right? Okay. But what are the challenges when we are trying to miniaturize everything and looking forward for some simpler solutions, specialized solutions using embedded platforms? One has to look forward for interfacing with sensors and actuators, as the block diagram also suggests. One has to look forward for its digital implementation. So when we are looking forward for the digital implementation, we look forward for quantization, sampling time, and digital computations, and its digital computations. So it requires a special effort in designing such controllers. And that's what the entire talk is based upon. So to begin with, let us understand what are the common kind of platforms available in the market, and we should look forward for using them in our robots design. There are microcontrollers, FPGA, DSP, and embedded Linux platforms, which are very popular, being used and are being used in robotic systems. But our main question is when to use which embedded platform, right? So that's what most likely you would be able to answer this once I finish my lecture, and I'll see I'll I hope I will be able to communicate that through this small lecture. So we have, starting with microprocessor, let's understand what are its capabilities and limitations, and based on which we should be able to say okay, what should and that would motivate for our choice. So when we see microprocessors, which are available in laptops or computing systems, CPUs, normal CPUs, servers, and so on, so these are typically used for the online programming. Yep. So of course it's general purpose, and one should be able to port one kind of program to another, and so on and so forth. So portability is not so difficult nowadays, because now even for microcontroller or other kind of FPGA programming, you use one embedded C kind of program, and then you look forward for cross compilers to look at. So there are many cross compilers nowadays available. So that's not a exact idea about using the general purpose processors, but yes, the computing part is very powerful here. So when your requirements are such that you are having very computationally intensive tasks to be done, image processing, GPUs are required, and so on, it's worth looking into taking the solutions to GPUs. Whereas when you have to look into some special purpose or customized solutions, one should look for microcontrollers, because what are the parts of the how is the microcontroller internal block diagram says is comprising of is it has a small ROM, small RAM, few timers available, serial port is available, IO port is available, and some small CPU part is available. So you will be able to do some reasonably good amount of computations there. So with that, you are able to interface the external peripherals very nicely with microcontrollers. So that's what is the major advantage you are able to get with the microcontrollers, because in the robotic system, we understood that we have to interface sensors and actuators, and that can be very well done with the microcontrollers. So that's how we can look forward for using microcontrollers. So which microcontroller to use, that depends upon the memory requirements, your IO port requirements, and what kind of peripherals you are looking forward for interfacing with this particular embedded platform. Coming to FPGAs, let's try to understand what's the internal block diagram of field programmable gate arrays. When we compare the FPGA with microcontroller, um, microcontroller is something where the hardware is frozen. Yeah, so you know that there are those many IO ports are there, and you are having that much capability of arithmetic and logic unit, 8-bit processor, kind of 8-bit operations can be easily done, and so on. Here in FPGAs, this particular hardware is right now not frozen. You program it for your ease. For example, you want 2 8-bit ALUs. You would be able to do it because each of the block diagram is a logic block. That logic block, you can understand it as a truth table, right? So this particular way, you would be able to define whether you want 16-bit operations for certain, for example, you want 16-bit adder subtractor. I'm sorry. but 8-bit multiplier. Okay, so you decide what you want and then program it in the digital hardware. At the same time, there are hundreds of IO boards available. IO pins are available. So you can parallelly connect multiple sensors, you can parallelly connect multiple actuators, and you can work around with designing your own digital hardware. What all specific things you want, you use that and program it in FPGA. Having said that, that you decide what kind of multiplier you want or 16-bit adder subtractor you want. It's not to that level, you don't have to go, because the high level programs are available like Verilog and VHDL, which constructs are similar to C language. As soon as you say that A plus B, you have to define what is the bit or word size of the A variable is, word size of B variable is. When you say A plus B, it will decide what should be that adder, what should be the size of that adder. So one should not worry about too much going into the digital hardware and looking into it. As long as you are comfortable with embedded C or C language, you would be easily able to program it into the FPGAs as well. But the advantage that we get here with FPGAs is about parallel hardware and processing. So one should not look forward for example, you are having quad core i7 processor. So you will be able to know you know that there are 4 cores available, right? Whereas here you can have as many you want, as much parallel processing you want. Of course, it's limited by its own size and so on. So you should be able to, so this is what is one step towards the application specific IC design. So you design everything in FPGA, then you will be able to port your hardware, digital hardware into ASIC kind of methods. So one is very sure that FPGAs are good for the real-time applications because of its parallel capabilities. And when the IO requirement is high, and when the IOs have to be parallelly read or parallelly you want to give the right commands to the actuators and so on. Look into DSPs now. Now, these digital signal processors are certainly specialized microprocessors for the needs of the signal processing. So this has a good computing powers, and for example, many DSPs support the computations of exponential logarithmic computations, and at the same time a lot of Fourier transforms or Laplace transforms kind of stuff is very easily can be easily done through the DSP blocks, filter designs especially, right? So one can look forward for using such kind, whenever there is some kind of such kind of applications are there which requires digital signal processing and filtering, one can look forward for DSP processes. Then there comes the category of embedded Linux, which is now very popular because instead of looking into the laptop or a CPU, which is having the complete Linux platform, these processors you should be able, so this is kind of a compressed software. I see the embedded Linux applications as the compressed software applications where you basically have the Linux kernel and then you build upon the application layer what you want, like in FPGAs. FPGAs, you are doing everything to hardware, whereas here you are having the same processor, but you should be able to bundle your software in a way what applications you want. So which part of the software you want, that you embed into the Linux kernel, then port it in and then program it in your processor. So that is again giving you customized solutions. Of course, you need coding skills, you need interfacing, but yeah, interfacing with the sensors is very easy because there is a lot of open source available on the software. You pick up that software which is compatible with your version, and then get going. That's the whole idea here of making everything open source mainly, right? But what is, when we look into these embedded platforms, what is the main bottleneck? The bottleneck is about doing all the computations in the digital way, such that you are doing manipulations only with bits, and bits as in you cannot, you have to make sure that you are having you should be aware about the limitations of these digital hardwares. Yeah. So when you are doing the fixed point, whether you are doing the operations with fixed point or a floating point operations, you should be aware about its limitations. For example, you have 10 bits of operations you have planned for, but in certain cases, you are having some operations such that it is requiring 11 or 12 bits. So what will happen is the condition of overflow, and then all your computations will go wrong. So that's the whole idea, is about knowing what your digital implementation is looking for. So what we can look forward for when we are specifically looking forward for the controller design, what we can look forward for two kinds of approaches, where we use special algorithms for the computing. There are many algorithms available which do complex computings as well in digital. For example, you have the exponential, you want to calculate exponentials, logarithms, sinusoids, and so on. So then one should be able to, there are algorithms available, and you should be aware about those algorithms. Instead of doing everything in a lookup table manner, you can implement sinusoids, calculation of sine using the lookup table method, but it requires memory and so on. So there are algorithms available even for this Fourier transform or any such kind of transforms for the signal processing. So nowadays in DSP, those blocks are currently immediately available, and you should be able to program the codes and so on. The second approach is to look into this interval analysis technique that I will be introducing to you, or you are already aware about. So let me give you um, a quick overview of the interval analysis. Okay, so I can stop here for 2 minutes if you have any questions, and uh, can take it forward. I mean, instead of making it one-way communication.
Right. Up till now, there are no questions, but dear participants, you can raise your hand and also you can write your questions in the chat box.
Okay, wonderful. So let me go ahead with the interval analysis method. So this is basically introducing intervals. It was introduced in 1966, sometime back, for defining. So basically, when you measure a physical quantity, you say that I am measuring temperature, for example, which is turning out to be a 98.6 degree Fahrenheit with an accuracy of plus minus 0.1, right? So you are having some accuracies. So you're basically saying that my measurement is bounded by this 2 degrees, 2 degree Fahrenheit, or if I say 0.2 plus minus 1 degree Fahrenheit. So it is bounded between these two values. So this is from the physical quantity measurements perspective, precision perspective, accuracy perspective. But when we look into the digital implementation, then you look into the quantization, and there are errors due to rounding and truncation. Yeah. So what is that bound? by which we can say precisely that this is what is the physical quantity uh, value is, value of the physical quantity is. Okay, so this is what the idea about the intervals. So why do we look into the interval analysis? There are two ways, two basically, it's kind of two types of uncertainties that you would like to bound it. One is the inherent variability, which I said, when you take the measurement itself is erroneous and you say that this is what is, how it is, it much precise. Sometimes you do not have the knowledge about that physical quantity. So if that is the case, then you can say that, okay, I have this particular large band available, and I'm very sure that the value of this particular physical quantity is within that bound. And that's why this particular representation of intervals do come in. So mostly these there are other ways of dealing with uncertainty also. So there are probabilistic approaches, fuzzy set approach, fuzzy set theory, and Damster-Sheffer theory. What we are saying is about interval analysis. Okay, so instead of looking into, for example, probabilistic method where you say that there's a mean value and then there's a standard deviation available, no. What we are saying is a kind of a deterministic way, that saying that, okay, this is what is my uncertainty into the calculations and so on. We use it in, when we do the digital implementation, we say uncertainty in calculation. Whereas when you take this particular interval analysis methods were introduced for the measurement purposes and so on. So what are the benefits with this when we define the intervals? So very best benefit that we get is that when we do this interval computations, we will come up with all kinds of solutions that are possible. Yeah, you will appreciate this particular comment a little later after you look into one of the ways where we have applied this. We don't have to look into running many stochastic simulations like Monte Carlo solutions and so on, because we know that we have given a confirmation that my solution lies within that particular interval. So, of course, when we are designing the interval methods, we have to look forward for when this is typically iterative method, and we have to look into saying that when to stop that iterations and so on, right? So let's not look into too much details of these parts, but you will appreciate I can these particular benefits later on once you are yeah, once you see one of the methods where we have applied the interval. So there are ways by which you can do interval analysis. Maple, Mathematica, MATLAB, all these methods do support the interval analysis, but we would not be using them. We will be rather designing our algorithms to calculate it iteratively and so on. So let me give you a gist of this particular one kind of function that we will be using it for defining the interval analysis, the interval functions and so on. So for example, I have a variable x, and this particular x is a variable in 2 dimensions, x1 and x2. So when I define the interval in these 2 dimensions, this will turn out to be a rectangular representation where we say that its value is between x1 lower bar to x1 upper bar, and in the x2 dimension, its value is x2 lower bar to x2 upper bar. Now, if I apply a mapping to say the y world, like where the dimension is given, where the variables are given by y1 and y2. So this mapping is with the help of this function. So if I apply this function f on this interval, on interval as in all values within that interval in x domain, I will end up in this gray area. Okay. But now the output that I'm looking forward is also to be represented in terms of intervals. So my answer should give me an interval in y domain which is bounded by certain limits. Yeah. Okay. So if I apply directly the function bounds, I may land up in a bigger value, which is not desirable. And that's why we should look forward for defining certain functions such that we are getting an appropriate bound, just enough bound for the all kinds of values within uh, the domain of this, such that um, you are basically moving to your the y domain. So your range values should be mapped to a bounded values in the y domain. Yeah. So that's what the entire idea. So design a nice inclusion function that's called inclusion function such that all values in x in that particular interval maps to an interval just enough bounds for that particular y domain. So let's look into such interval computations. So interval analysis can be used for defining the completely the true values and so on. Let me not let me skip this particular um, slide and see where else this particular interval analysis is used in robotics. It's being used for defining the manufacturing tolerances, sensor uncertainties, safety and guarantee situations, and finite time, inverse kinematics, because we are talking about all possible solutions, motion planning, simultaneous localization and mapping, and we applied for collision detection and avoidance, and that's what I am going to introduce you to. Right. So here comes how we have applied the interval method. So I have told you that, for example, given a pictorial representation of a two-dimensional interval, which was turning out to be a rectangle, if I define, whereas if I define the interval such that it's representing the polar coordinates. So there is a lower limit on r, upper limit on r radius, and then lower limit on the angle and the upper limit on the angle. So with respect to this particular xy coordinate system, my interval will look like uh, uh, some section of a circular disk, A, B, C, D, right? Because my interval describes the lower limit of the radius and upper limit of the radius, then lower limit of theta and the upper limit of theta. So this way, some way the position of the robot can be described by saying that, okay, I am somewhere in this particular xy uh, system, this particular xy coordinate system, which is where the position of the robot is described by this particular circular section of a circular disk. And that is described by this particular interval RL, RU, theta L, theta U. So let's see, instead of using the position, what we have said is, for example, I'm starting with this particular position here. This is what is my current location of my robot. And it is having going by the nominal velocity Vr and nominal angular velocity omega r. For example, it can change its velocity by delta Vr and delta omega r. So in the delta t time where it can land, it can land anywhere in this particular sector of the circular disk. Similarly, if I describe a dynamic obstacle in the delta t time, if the current position is this and its velocities are given similar to what the uh, robot velocities are there, then in delta t time, it will take up this particular circular sector. Yeah, and this is how we define the intervals for each of these uh, uh, location, either robot or the dynamic obstacle in delta t time. So now I have to find out whether they will be colliding in this particular delta t time. Yeah. So if the robot is having this particular interval, for example, an obstacle is having this interval. So we have to look forward for its intersection. And then with respect to the robot, we have to define its interval. Yeah, so that's what the objective is. Now, if the intersection is known, then I should be able to claim very well, find out what is the collision free interval. And this collision free interval will tell me which are the velocities, permissible velocities of the robot, which are not going to collide with the obstacle in that delta t time. So let's see how we did this. A very quick pictorial way of looking into how the iterative algorithm was developed. So we do this branch and bound algorithm, which does the bisection with respect to r, and this does the bisection with respect to theta. So see how it goes. So if we do the bisection with respect to r, then this particular green one is not at all intersecting with the obstacle interval. So we will discard this and we'll deal with only this interval. Whereas when we bisect with theta, what happens is both the intervals are having intersection with the obstacle interval. So then we'll keep both of them into our consideration. So next iteration, you look into these gray ones here in the with respect to theta, both the intervals. You do further bisection with respect to r. For this particular one, again, these two intervals are having the basically we test the inclusion, and inclusion of that interval is yes or no. If it is yes, keep it, no, then discard that interval. So what happens is you keep on doing this way. So which one is, so for example here, the dark blue one will be discarded. And similarly, the sky blue one will also be discarded because this is not on the boundary side, right? So the interval ones will keep, each iteration will either work with one interval or two intervals, and keep doing it such that you reach almost to the boundary of the intervals. Okay, so this way, so when you have reached to a very small strip, you can stop. As I said, we have to have some kind of a stopping criteria. So here I'm stopping it. So as soon as you get the lower and the upper boundaries of the interval for the intersection, that is what the objective was in r and theta. So you keep those intervals. Now those intervals are basically defining that if you go only the with r, you will come up with this pink color interval, whereas when you do the bisection only with theta, then you'll land up with orange. So you combine both the information and you come up with the interval, which is basically defining what is getting, which interval with respect to r is getting collided with the obstacle interval. So this way you are able to segregate the collision free interval and so on. So let me just take you to this particular video will tell you how we use this particular interval method for doing the collision avoidance with multiple robots now. Why we are saying multiple robots in parallel? Because we designed this particular algorithm such that it is doing the bisection. And this bisection is doing only the addition and subtraction and division by 2. So it is well suited for digital computations. Division by 2 is nothing but shifting right by ones. So you could do the FPGA implementation here. As soon as it is FPGA implementation, and I know that there are those many dynamic obstacles or those many robots in the environment, I can have those many parallel blocks. And each of this parallel block is now giving me an interval, which is collision free. And I will combine these multiple collision free intervals to come up with single interval, which is completely saying that for that particular robot, this is what is the collision free interval and this is what is the velocities which are permissible and basically which are not colliding with that particular robot. So this way, when you are developing an algorithm based on certain technique, you know that you will be nicely able to implement in an embedded platform which you have chosen. So here we started by knowing that we want to do multi-agent collision with using FPGA. So that's why the algorithm is designed such that it is using only addition, subtraction, and division by 2, right? Okay, so let me go back to my presentation. I hope you were able to see my video. When I'm switching the screen, you are able to see the video.
Yes, ma'am.
Yeah. Okay. So let me. So this was the design methodology using the interval method. Now I'll quickly go into the bottom-up approach. I'm just having 5 minutes left. So I'll tell you a controller design which is rigorously analyzed using nonlinear stability method. But now in this particular approach, we will look into designing the controller such that I'm using minimal computations. But the theoretical background is such that it is completely saying that okay, my controller is stable enough to be looked into. Now, since my computations are small enough, what we will say that it is suitable for implementing in any embedded platform. So even in the microcontroller, I will be able to implement it without any worries of whether it is quantization problem. I don't have to look into the quantization and the other issues because the computations requirements are very, very, very minimal. So with that objective, we start by this saying, we designed this particular algorithm for spherical robots, but it is actually applicable to any unicycle method. So we designed this algorithm to say that you have only 3 actions available. One is to go straight line, steer left, or steer right. Okay. And of course, since our measurements are limited, it will have only position measurement available. So this particular state variable description is again in the form of the radius and basically in the polar coordinates. But the entire idea here, I will just simply speak about the idea and not go into the mathematics and further details of it. For example, you want to reach to this particular origin. So this is a navigation task. You are starting from this position P with an orientation V, and your objective is to reach to this particular point O. And let's say the current velocity vector is given by this particular arrow uh, with the v vector sign. So what we will look into is that if this particular vector is such that it is in this particular quadrant or in this particular this with respect to this particular line OP, if your vector is above it, then you will be turning left. If it is below it, then you will be turning to the right side. And if you are exactly aligned towards this OP line, then you keep going in the straight line. Yeah, so that is what the only idea which we built up. Now, why is it important for a spherical robot? Because if you look into the footballers who do the movement of the ball to go in certain direction, they do nothing but dribbling using their left and right foots, and that's what exactly we did here. You go left or right if you're going away from this particular OP line. Yeah? So that's the entire idea. But with the particular nonlinear analysis, we could say that this particular system is stable. And you see that what we used here is the linear velocity is constant and the angular velocity changes its sign, whereas rest of the other quantities are constants. So whether you go right or left, depending upon where your position turns out to be with respect to this OP line. So we did some outdoor experiments also. Um, I hope it will quickly start. So this is the autonomous navigation. So this student is only recording, is not doing anything. The GPS is used for recording the position, and the current and the previous GPS location gives some estimates on the orientation of the part, and this student is only recording the closer look of this particular robot, and you can see here that it is doing nothing but wobbling, going left and right, that's it. Yeah. And then it is supposed to reach within this circle of this destination point uh, here. So this particular circle also, we could claim it very clearly that if there are orientation errors and sensor errors given by this bounds, then this particular where you will land up will be able to tell based on the estimation bounds on the estimation error and the measurement errors. All right, so let me go back to my presentation again. And this is the last part of the uh, uh, application, which is nothing but swarm aggregation. Now, what we did here is use the same control law that I explained going into left or right direction. This aggregation method is used for a group of agents. So we combined the idea about the control law that we designed and the interval method for the collision avoidance, right? So what comes up here? Let me just quickly tell you. For example, this is what is, so now you are dealing with group of agents and you want to reach to a destination. All the agents should reach to a destination, and you are aggregating your swarm to reach to a particular destination. Uh, and at the same time, we said that these agents are not communicating with each other, whereas each of these agent is able to see, is having some sensor which is able to see within that particular field of view if there is any other agent or not. So in this field of view, if there is an agent turns up, then, so for example, let's start with this particular jth agent. In this particular field of view, there is no agent, so it will go into this particular destination. So that's called the free subsystem. For example, you are in the, you're talking about ith agent. Then this ith agent is having jth agent in its field of view, and there is a possibility that it will collide with jth agent. So it will be in the engaged subsystem, where the control law will be the combination of repelling from this particular agent and going towards this. So both the objectives, right? So for example, you are in the free subsystem, then your particular control law, which is the steering control law, same as the one that I have shown with respect to the spherical robot. But if this is part of the engaged subsystem, where you are having, so all the four diagrams are for the engaged subsystem, where the field of view is having one another robot here. So then this green color one is the control law, which is basically same as the going towards destination, whereas it is having couple term, which is basically doing the repulsion with respect to that particular agent. So these green color and these red color ones make four such combinations, whether you are both of them are in the same direction or in the opposite direction, based on which we came up with the control law, and which says where we have to state that the system is stable for the free system subsystem, yeah, so which we have already shown it in one way. Then we had to show that the system is stable in the engaged subsystem. And then, since there is a switching between the free and the engaged subsystem, then one has to look forward for giving the stability at the time of switching as well. So these three stability conditions shows that this particular simple control law is able to do the swarm aggregation without communicating between the agents. What's the outcome? See here. Now you could see that that was a simple control law. The motivation was to design into the embedded platform, and that's why it turns out. So what it is doing is basically you are having multiple agents, multiple robots starting from different places, and they try to come and merge at one place. This is like the fishes, the school of fishes coming when you put a food particle into a pool or a pond, then these fishes come and gather towards it. And certainly when they are not reaching to a food particle, they might not be communicating with each other. So that was the initial motivation to mimic such a system. So this red and green color ones show that the red color one is basically in the engaged subsystem, whereas free ones, they are still looking forward for this. Since the stability was already proven, we perturb these some number of agents. They were able to do once again come back to that particular way. So the idea here is that theoretically, if you are strong, you will be able to apply to multiple places. At the same time, this particular one, agents were, the entire control design was such that it is very simple and you would be able to implement on any simple embedded platform. So approach here was not to see that which platform to use, but to design a control law which is simple enough to be implemented on any simple microcontroller as well. And once it is microcontroller, then you can have microprocessor or FPGA or whichever way you want to look for. All right, so that's how I wind up my lecture. For the swarm aggregation, there are many other unsolved problems to look into. You can look forward uh, for analyzing the behavior of heterogeneous agents. Right now, we consider each and every agent is same, and each and every agent has the same control law being implemented. One can look forward for hijacking the target because that is moving towards one single target. And for example, that target location itself is disturbed. That's how the cybersecurity and so on are being so much in talks nowadays. So concluding from the embedded system perspective, we can see that there can be two approaches for the embedded implementation. One is, one should follow such that your controller design turns out to be very simple. And then one can look forward for designing specific algorithms which are basically designed for specific embedded platforms, right? So these two ways you should be able to address to the limitations of